Solving general chemistry problems. Reaction kinetics. What is a chemical reaction? For a reaction to occur, two things, atoms, molecules, ions, must bump into each other. There has to be a collision. And it matters how hard they bump into each other. We call that kinetic energy. Too slow or too fast. Both can keep something from happening. And they have to be oriented just so at the moment of that collision. And the alignment of the collision has to be appropriate, right in the middle, well off to the edge. And if there are two or more atoms in one of the things colliding, the way it is rotating and the way it is vibrating makes a difference. When all of the nuclei in the reaction get close together, that's the collision, the electrons can try to quickly rearrange themselves. They're much lighter and move much more quickly than the atoms can. Old bonds are broken, new ones are formed. If the new arrangement is stable, the atoms separate with the electrons holding them together in a new way. Products have been formed. For some reactions, these demands are stringent and most collisions do not lead to a reaction. For other reactions, these demands are more relaxed and a larger fraction of all collisions are successful. The difference in the details leads to some reactions occurring very quickly, like an explosion, for instance, while others are occurring very slowly, like the rusting of an old car body in a vacant lot. Understanding how quickly or slowly a chemical reaction occurs is the study of reaction kinetics. Studying some more of these minute details of the collision events is called reaction dynamics. In general chemistry, we largely focus on reaction kinetics, though we will take some baby steps into the deeper end of the pool. So what does it mean to study reaction kinetics? Clearly, we are interested in the rate of a reaction. How does a reaction proceed with time? Is it fast? Is it slow? And fast or slow compared to what? What influences the reaction rate? Does it change with concentration of reactants? Does it change with temperature? Is a reaction's rate always the same, or does it change as the reaction proceeds? One well-studied chemical process involves the reaction between bromate and bromide in an acidic aqueous solution. The first study of the kinetics of this reaction goes back to 1899. Pour in an aqueous solution of sodium bromate. Pour in another solution of sodium bromide with some acid in it. Stir it up and watch what happens. At the beginning, the solution is clear, but it slowly starts to develop a dark reddish tint, which gets darker with time. This is the bromine being produced. Apparently, the reaction products are bromine and water. We could use the color of the solution as an indicator of the progress of the reaction and use this to create a graph. Under certain conditions, we could follow this reaction for a couple of days. It can be quite slow, and we could produce a graph like this one. Notice how at the beginning the color of the solution is changing quickly. It's getting darker quite fast. But once it gets darker more slowly. The reaction is quick at the beginning and then slows down as it reaches the end. With some careful spectrometric work, we can relate this to the concentration of bromine and, for these conditions, create this graph. Note that we had to watch it for 150,000 seconds, which is starting to approach 2 full days. Now this is a redox reaction. The element bromine shows up in 3 different oxidation states. What are these? Well, first of all, Br2 is elemental bromine, so in that molecule, the oxidation state must be 0. In bromide, the single atom's oxidation state must be the same as its charge, which is -1. Finally, in bromate, the oxygens are all -2, so an overall charge of -1 means that the bromine must be +5. With that, can you balance the reaction equation? I'll treat the oxidation and reduction half reactions separately. Well, elemental bromine is the product, so bromide must oxidize to bromine, and bromate must be reduced to bromine. The oxidation reaction is readily balanced. Double bromide and add 2 electrons to the product side. For reduction, double the bromate to balance bromine. Add 10 electrons to the reactant side to account for the change in bromine oxidation number from +5 to 0 for 2 bromine atoms. For the reduction, add 12 H pluses to the reactant side to balance charge. Add 6 water to product side to balance oxygen and hydrogen. Multiply oxidation by 5 to equate the number of electrons. Add the equations together, divide by 2 to minimize the coefficients, and finally obtain the balanced equation. What does this equation tell us about the thermodynamics of this reaction? Well, quite a lot actually. With formation data, we can find delta H naught, delta S naught, delta G naught, and from there we can find K, the equilibrium constant, and E naught, and if we set it up in a cell. And what does this balanced equation tell us about the kinetics of the reaction? Not much at all. Now, this is an important thing to remember. The balanced overall chemical reaction equation tells us nothing about the kinetics of a reaction. We must perform carefully designed experiments to determine kinetic information. It should perhaps be obvious that while the balanced equation tells us that 1 bromate, 5 bromide, and 6 hydronium ions are converted into 3 bromine molecules and 3 water molecules, we must remember that it does not imply that a bromate ion, 5 bromide ions, and 6 H plus ions suddenly bump into each other and magically produce 3 bromine and 3 water molecules. The chance of such a collision between 12 molecular entities when they're all moving randomly and independently is vanishingly small. Now we can imagine a collision between 2 species. That should be easy to arrange. We would call it a bimolecular collision. Maybe even 3 at the same time. We would call it termolecular. But it's more likely, even in that case, to envision a sequence of 2 bimolecular events, an initial collision, then before they separate, a collision with a third body. Well, maybe that can happen, but if you try to arrange for anything greater, it is increasingly unlikely. A chemical reaction consists of a series of bimolecular, and if you must, the occasional termolecular collision. Sometimes a collision occurs that excites a molecule, meaning an increase in vibrational and rotational energy and motion, but doesn't break any bonds. The excited molecule may wait for a little while, nanoseconds, microseconds longer, perhaps, and then it suddenly undergoes a reaction that does break some bonds. We call this a unimolecular reaction. All of these collisions together must add up to the overall balanced chemical reaction equation. We call each of them an elementary reaction step. Each of these steps does have some important kinetic information associated with it. Often one step may be the slowest one that ends up controlling the overall reaction kinetics, but such insight comes only from experimental results. We can, and indeed we must, add together their elementary reaction steps to get the overall balanced equation. But we cannot derive those elementary steps from the reaction equation alone. Experimental kinetic data is required. So let's take a bit more a closer look at some of this experimental data. Now we're still looking at this bromate-bromide reaction. This is the same graph we saw earlier. It tells us the way that the concentration of bromine changes with time. And this is an excellent proxy measure for the rate of the reaction. But first, what do we mean when we say rate of the reaction? Well, the reaction is the balanced equation we are referring to here at the top of the screen. While we make no claims about the detailed mechanism, we are confident that every time a bromate is consumed, 5 bromides are also consumed and 3 bromines are produced. The stoichiometry still holds true, so I guess it's a little unfair to suggest that the balanced reaction equation gave no kinetic information. Its stoichiometry is indeed helpful. Whatever the rate at which bromate is disappearing, we know that bromide must be disappearing 5 times faster. And we know that bromine must be appearing 3 times faster. Now the negative sign is here because the bromate is decreasing while the bromine is increasing. And we didn't need the sign in the statement above because both are decreasing. What is the rate of the reaction? Well, we might answer it as how many times per time unit, let's say per second, does this reaction occur in the entire reaction vessel? If there are a lot of them, and since molecules are involved, it probably is a lot, we could say how many moles of reaction events occur per second. Now, this would depend upon the size of the reaction vessel. So a bit more useful measure would be to ask how many moles of reaction events occur in a liter of reaction solution every second. Now, this is perhaps the best approach. Our rate of reaction will have units of moles per liter per second or molarity per second, molar per second. The rate of reaction is how many moles of reaction events are occurring in a liter of reaction solution every second. Molar per second is the standard way of reporting a reaction rate in a solution. It would also work for reactions in the gas phase. Reactions at a surface would need to be changed, but the concept is the same. We will not look at surface reactions in general chemistry. We can just focus on molar per second. Now remember, when we are talking about the rate of the reaction, we are not talking about bromine or bromide or bromate. We are talking about the reaction as written. The stoichiometry relates the reaction rate to the rate of the appearance of bromine or the disappearance of bromide or bromate. But be sure to keep the distinction in your mind. We might find it hard to measure reaction events directly. Instead, we can come up with many different methods to measure the concentration changes of some of the reaction participants. There are many techniques that have been developed to measure these concentration changes. For general chemistry, let's just assume that we have been able to make those measurements and leave the details of how it is done for a more advanced course in reaction kinetics. So look at this graph. Again, a bromine concentration versus time. What is the rate of change of concentration of bromine? Look at the first 20,000 seconds. Just from the graph, it looks like the concentration goes from 0 at the beginning to about 2 millimolar. And if we look at the data table from which I made the graph, we'd find that it was actually 2.05 millimolar. So in 20,000 seconds, the bromine concentration increased 2.05 millimolar. We would say that the average rate was 2.05 times 10 to the minus 3 divided by 20,000 equal to 102.5 nanomolar per second. This straight line connecting the beginning and end of the period represents this average process. So what happens during the next 20,000 seconds? Now from the graph, it seems that the concentration increases to about 2.45 millimolar, which is a good estimate. The table gives 2.449 millimolar. During this time, the concentration increases 2.45 minus 2.05 or 0.4 millimolar. So the average rate of increase in concentration is 0.4 times 10 to the minus 3 divided by 20,000 equal to 20.0 nanomolar per second. That is about 5 times slower than during the first 20,000 seconds. The next time period, concentration at 6,000 seconds is 2.64. 2.64 minus 2.45, 0.19 times 10 to the minus 3 divided by 20,000, 9.5 times 10 to the 9.5 nanomolar per second. I think you can start to see that the rate is continually slowing down, but if left long enough, it might finally stop. What if we were to look at shorter time intervals? Instead of 20,000 seconds, what's the average rate during the first 10,000 seconds? Well, from the data table, it's 1.59 millimolar, so the average rate 1.59 times 10 to the minus 3 divided by 10,000 equals 159 nanomolar per second. And then the next 1,000 seconds would be 2.05 minus 1.59, 0.46 times 10 to the minus 3 for a rate of 46 nanomolar per second. I think you can see how this can continue. If you are currently enrolled in a general chemistry course, I suspect that you are also enrolled in a calculus class. If so, you must recognize that this move to smaller time intervals is just what one does in differential calculus. Hopefully you therefore recognize that the slope of this curve at any point is the rate of change of that curve at that point, and that this is the derivative. The rate of change of bromine concentration is the derivative of the bromine concentration curve with respect to time. It has these units of molar per second. Then what is the reaction rate? Well, it is the derivative of the number of reaction events per liter, the concentration of reaction events, with respect to time. It has units of molar per second also. We can experimentally determine the bromine concentration changes with time, but not the reaction rate directly. How do we relate the two? By the reaction equation stoichiometry. The bromine product must be exactly 3 times the reaction rate. Every time the reaction occurs once, 3 bromine molecules are produced. We just divide the bromine rate by 3 to get the reaction rate. Experimentally, we might be able to measure the concentration of some of the other reaction participants. If we measured bromate, its rate would be the same as the reaction rate, stoichiometry is 1, except that bromate decreases, so we would have to change the sign. A reaction rate is always positive. If we measured bromide, we would have to change the sign and divide by 5. Hydronium ion, change the sign, divide by 6, and so forth. This is the key to connecting derivatives of concentrations to the rate of a reaction. For the general reaction, AA plus BB goes to CC plus DD, we can write the following. Note how we divide the concentration derivatives by their stoichiometric coefficients, and we insert the negative sign in the case of reactants. Our experiments can measure concentration changes. This relation allows us to convert those measured derivatives into a rate for the reaction itself. Now, just to come full circle on this particular bromate-bromide reaction, here are the specific starting concentrations for the reactants. And here is the bromine curve, the one that we've been studying so far. Now, before I place the bromate and the bromide curves on this same graph, pause the video and see if you can estimate where they will look, what they'll look like, and where they will start, where they will end, and what will be the shape in between. Thinking, thinking, thinking. And here is the bromate curve, and here is the bromide curve, and here is the hydronium ion curve. So how did you do? Why does the bromide curve go to 0, but the bromate and hydronium ion curves do not? What change in initial conditions would change this so that bromate goes to 0 and bromide does not? What would these conditions need to be for both to go to 0? So this is all just about limiting reagents. Bromide is all used up, so it is the limiting reagent. The reaction slows down and begins to stop because it runs out of bromide. If we were to start with a lot more bromide, say 0.02 molar, then bromate would be limiting. And since the stoichiometry between the two is 5 to 1, if we start with exactly 5 times as much bromide as bromate, then they will both go to 0 as the reaction slows down and finally stops.